Hello and welcome to another video. In this video we're going to be doing binary tree with factors. And in this problem you're given an array of unique integers R where each integer is strictly greater than 1, and you need to make a binary tree using these integers where each number may be used for any number of times. Each non-leaf node's value should be equal to the product of the values of the children. Return the number of binary trees we can make. The answer may be too large, so let's just return it modulo 10 and 9 plus 7. So in this first example we have 2 and 4. And the trees you can make is tree with just node 2, tree with just node 4, or like this, 4, 2, 2. And in the second example, so you do have all these trees that are just one node by itself, but other than that, you can also make 4, 2, 2. You can also make 10, 2, 5, and 10, 5, 2. So notice that like these are two different trees even though they are using the same values. So that's one thing to keep in mind, is like you have to keep in mind both combinations. Now the wording for this problem is a little weird and a little confusing, where they say each non-leaf's nodes should be equal to the product of the value of its children. So that just means like it's two children right above it, not like the whole tree below it. So if you have some node like this with a bunch of nodes here, it's not like this node's value should be equal to the product of all of these. It should only be the direct children. Because at first I read it and I thought it was all of these, and I was just like, okay, this is going to be like a really hard problem to do. But if you're just keeping track of the two children, then it makes it a lot easier. So essentially what we have to do is, like, let's say we do have this array 2, 4, 5, 10. We can even have a few more, I guess. So let's just have 2, 4, 5, 8, 10, 16, let's say. So essentially, for one thing, you know that like you're going to have to consider trees with every single one of these nodes as the root, right? So you are going to have to like loop through this whole thing, and any one of these can be the root. But what else do we need to know? Like, let's say we're considering a tree with 5 as the root. Well, so notice how what we can do is we can sort these to make it in increasing order, and then that way, when we look for factors, like let's say we're looking for this node, so if a node has 8, the left and right child have to be factors of it, right? So like these two nodes have to multiply to be 8. So what we can do is we can simply know that like whatever index we're on, we only have to check the left side, because anything up here can't be a factor. And then we just have to check value by value, and if we find a factor, let's say we find a factor 4, we can figure out like what the other factor should be, right? So if we find a factor 4, we can figure out, okay, the other factor needs to be 2, and it's 2 in here. And the way we're going to do this, actually, is we're just going to create a mapping of every node to its index. That way we can get these really quickly. So we're going to essentially have some root, and then we're just going to go value by value and say, like, okay, if this is a factor, what should the other factor be, and where is it? And let's do the DP there. Because in our DP, we're actually going to DP by index. So that's why we're going to create a mapping. Now you could also create a mapping of every product possible, and you could say like, okay, let me get every product possible, and then let me check if a product is actually one of these nodes. So like, let's say I'll do like 2 times 4, and then I'll check like, is 8 actually in these? And then I'll store that. But then that's going to make your space complexity worse, essentially. So you could do one, you could do the other. Actually, maybe it won't do it worse if you... It might be no. It'll still not be great, yeah, because you're gonna store a bunch of nodes in the same product. So I think it will actually be worse. But then your lookups will be faster, because then like for 8, you can say like, okay, well, let me just look for all products of 8, and then I'll just have like a list of nodes that multiply up to be 8. But that is a little bit slower, space complexity. But in time and practice, it should be a little bit faster. So that's like slight performance things there. But what we're gonna do is we're gonna just manually look through the left, and then anytime we find a viable factor, we'll see if there's another factor. Now, for a node, let's say we have node 8, and let's say we say, okay, we found two factors, 4 and 2. So how many trees can I make with this combination? And so the number of trees you can make with this combination is the number of combinations you can make with this being the root, and the number of combinations with this being the root. So let's say I can make like 10 trees with 4 being the root, and I can make 10 trees with 2 being the root. The total combinations here is going to be 100. So it's however many trees you can make with the left times the right. So we can write that down. So total trees given two factors equals, and we're going to use dp here, dp of left times dp of right. Because basically, yeah, like it's just like a combinations problem, right? If you can have 10 different ways of making a tree here and 10 different ways of making a tree here, how many total trees can you have? You can have 100. Because for each one of these, you can have 10 here, right? And there's 10 times 10. So for every factor, this is going to be the case. And now there might be multiple factors that are actually viable. So for 8, let's say we have 4 and 2, but let's say we had some other factors. Or let's say we actually have 4 and 2, but we also have 2 and 4, right? So, and let's say there's 10 of each of these. So this would be 100, and then 2 and 4 would also be 100, so then you would get 200. So for every set of factors, you have to figure out, like, we're just going to keep track of, like, how many nodes can we make on the left, and then how many nodes can we make on the right, and then we're going to multiply them together. Because for this tree, both of the factors, like, you have to have pairs of factors, right? So you have to have, like, 4 and 2, or 2 and 4, or whatever other stuff. You can't have, like, 4 and 5. So that's going to be kind of like our recursive case, where we're just going to look for factors. And we're going to say, okay, if both factors exist, let's recurse. And then the number of ways you can make this tree with this root and these two factors is left times right. And you have to keep adding these for every single factor. So you have to do this for every single group of factors that you have. Yeah, and that's roughly it. So essentially we can write down our logic again. So first of all, create dictionary with value and index, just so we can get indices of 1, right? Then we're going to do a dp. And so our base case isn't really, our base case is basically we have no factors. And so also keep in mind, so let's say we have no factors. So how many trees can we make? Well, if you look at the example, you can always make the tree with just the root and no children. So we're going to initialize our result to be just the root and no children. So like whatever thing we're at, we're going to say, okay, so if we're at this, we're going to initialize our answer to be 1, and then we are going to look for all factor combinations and add it here. So dp with cache, obviously. And for each factor, for each, not factor, for each valid pair of factors, get dp of each and add dp left times dp of right, because that's the number of total combinations. And you do have to make sure that, like, also, if you have a number like 4, so 4 can have 2 and 2, so you can use the same number multiple times. So, like, this is a valid answer as well. And then this would be the number of ways you can make a tree with 2, and the number of ways you can make a tree with 2, which would be the same. So let's kind of walk through what this would look like with this, essentially, just to do like a dry run of this kind of thing here. Okay. So essentially what we are going to do is we are going to loop, right? We're going to loop through every single index. So we'll start with 16. So 16, what are all of its factors? Well, one valid factor, C, is 8 and 2, right? So 8 and 2, okay. Actually, let's do it left to right, because that way we're going to have these values computed already, right? That'll make it easier for us to compute all these things. So let's start over here. So for 2, there are no factors, right? So this should just be returning 1, right? Just the root. Then for 4, what are all the factors you can have? Well, you can only have 2 and 2. And how many ways can you make a tree with root 2? Well, just once, right? We have it saved over here. So we can either make 4 or 4 and 2 and 2. So this is going to be 2, right? For 5, there are no factors. So this is just going to be 1. For 8, now we can have that just the 8. We can also have 8 for 2. So how many different ways can we do this? Well, 4 we can make 2 ways, and 2 we can make 1 way. So there's 2 ways you can make this tree. And there are also 2 ways you can make this tree. So that's 2 plus 2. And I believe that's it. So 2 plus 2 plus this original, just 8. So this should be 5, I believe. Okay. Hopefully my math is right there, but yeah. But even if my math is wrong here, you kind of like get the idea of what we're doing. So for 10, what factors can we have? Well, the only ones we can have are 2 and 5. And how many ways can we make 2 and 5? So there are only 1 of each. So this is 1 combination. Then we can also have 5 and 2, right? For every factor, you have to consider it both ways. One combination here and just the 10 by itself. So we have 3 here. Keep doing that. Okay. Let's just do it this way. Okay. And now finally we have 16. So what factors can we have for 16? So we can have 2 and 8. So for 2 and 8, we have 1 way and 5 ways, it looks like. So there's 5 ways of making this. Then we also obviously have 8 and 2, 5 ways of making this as well. So 5 plus 5. Then we also have 4 and 4, only 1 way of 4 and 4. We don't want to count that twice. 4, there's 2 ways, so there's 2 here, 2 here. So there's 4 ways of making this total, right? Left times right. Plus we just have the 16 by itself. So I think we have 10 ways of making a tree with 16, I believe. So we have 10 here. And I'm just not showing the subnodes, but yeah, like for this 4, you will have subnodes and so on, right? I just didn't show those. Because for this 4, you could have 4, you could have 4, 2, 2, and so on, right? For each one of these is the same thing. I just didn't draw all those. But essentially, we're just keeping track of like how many ways can we make the top level thing. So for the 16, you'd make 10, then you would add all of these up. And so you'd have like 18, 22, I think. Maybe I did the math wrong somewhere, but you kind of get the idea, where essentially you are just going to be looping left to right, and then you are just going to be adding all these up. And the way to figure it out with each set of factors like this is the number of ways you can make the left times the number of ways you can make the right. Okay, so now we kind of did that, so now let's actually code it up. We should have everything we need. So we're going to have the mod, because we are told to divide by this, so 10 to the 9th plus 7. Then we're going to sort our array, because whatever index we're on, we can just check to the left. So now we're going to have this like locations dictionary, so we can have val as the key, and the value will be the, or the index will be the value for I val in enumerate. Enumerate R. Okay. And we'll also have our visited cache for our DP. So now we have our DP. It's going to take an index, and and if the index is in visited, let's return visited index. Then what we're going to do is we're going to get the value, right? That's at that index. So we'll say value equals our index. And then, so our result here is going to be 1. So we can just call it like ways, as like the number of ways we can make the tree. So ways is going to be 1. That's going to be our initial case where we just have that node with no children. And now essentially we can loop through every possible factor. So we're going to say for factor 1 in array, and we're going to check every single index up to the current index, right? Everything to the left. So we're going to check factor 1, and then we are going to check for factor 2, right? So we can say factor 2 equals value mod factor 1. Now we do have to check like if this factor 1 is actually a valid factor, so we can do that as well. Actually, we can probably even write it in here. So we can just say like if value mod factor 1 equals 0, then this is valid, right? Then we can get a factor 2. Actually, no, I think it is better to do it here, because even if this is invalid, then we can check for both of these. So let's write it this way so we can get factor 2. So if factor 1, if value does cleanly divide factor 1, then factor 2 will also be a clean integer. So you have 2 clean integers. So if this is an actual factor and factor 2, we actually have it, right? Like whatever the second factor is, if we actually have it in our array, then we can add these factors to our result. So we can say ways plus equals dp of location factor 1, right? We want the index times dp of location factor 2. So essentially we get the index of both, and we figure out how many ways can we make the left times the ways we can make the right. And then finally, we will add it to visited. So we'll say visited index equals ways mod, just to keep the number smaller, and return visited index. So now that we have this DP function, now we just have to loop through every single number in our array, because every single number should be a viable root. So we'll say result equals 0 for I in range length array. let's just say result plus equals DPI. And finally, let's return that result mod because we want to provide a number that's modded by this to make sure that it's small enough. And yeah, I think that's fine. So essentially the idea is just get two factors and make sure they're actually valid factors, make sure they're both in there, and then if they are, recurse in, and we have a pretty good solution. So let's talk about the time and space for this one. It's a little bigger. Okay. So for the time, we are sorting, which is on log n already. Right. Now we are going through every single value in the array, that's O of n. Now this DP, so worst case scenario, you're actually looping from right to left from whatever index you're on. So actually, if you're on like the rightmost index, this loop will loop through the entire like array. So this will be n squared. So this is going to be n squared, and then yeah, all this is O of n, so that's fine. But essentially, this is an n squared solution. And then for the space, so we are keeping track of this like object for all of the locations, and then our recursive call stack. I think our recursive call stack can go down probably roughly. I think it can actually be like around n levels or something, because essentially you're taking two nodes at a time. Yeah, I think it's roughly around there. So I think you can go roughly n levels, but either way, because this is n, this is already n and also visited for every single index. That's already O of n. So the recursive call stack's not going to get worse than that. And this is already O of n. So this is just going to be O of n. And yeah, so not too bad of a problem once you realize that, yeah, this wording's a little weird and you just need the product of the children. Then you just need some kind of efficient way to find your children. And you're basically, I mean, it's not really super efficient, right? You're basically literally just looping through your array manually to find factors. As long as you can find the other factor efficiently, as long as you don't have to like find one factor and then find another factor by looping through the whole thing again, because that would be like an n squared solution. But that's pretty straightforward to just keep track of like a set or an object or whatever you want of numbers to make sure the other factor is actually in your array, because these are all unique values. But yeah, so that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.